Hey everyone! Today we'll be talking about orthogonality of the four fundamental subspaces of a matrix, and with this we will complete our picture and our fundamental theorem of linear algebra. Before we can move into the subspaces, first let's define what does it mean for two spaces to be orthogonal or two subspaces to be orthogonal. So here's a definition of orthogonal subspaces. So let's have two subspaces. So let V and W be subspaces of some space U. And here by space I mean a vector space and vector subspaces. Those are the only kind of spaces we'll be talking about in this class. So we have a U and now we have a V and a W, which are subspaces of some vector space U. Then we say that V is orthogonal to W, and I'll denote it in this standard way of orthogonality. We've seen this in our perpendicularity in geometry many times, so I'll just use this notation. We'll say that the subspaces V and W are orthogonal if for every V in V, so for every vector V in the first subspace, and for every W in W, we have V transpose W is 0. Okay, let's unpack what this means. So imagine here is the space U, and here is the space. So we remember every subspace must contain 0. So we'll have maybe here will be the space V, and somehow here will be the space W. I'm not saying they're planes, but it's important that they only intersect at the origin. And the reason for that is that if I take some vector V in here, and if I take some vector W in there, then those two vectors are going to be orthogonal. And that's what V transpose W, this is just another way of writing the dot product between V and W. So if the dot product between V and W is 0, that means that the two vectors are orthogonal. So when do we have orthogonal spaces? When every vector in the one space is orthogonal to every vector in the other space. So what are some examples of orthogonal subspaces? So let's talk about examples of orthogonal subspaces. Well, the easiest thing to think about would be taking R3, so 3D space. Let's have a picture of that. So we could draw any vector like that. And so let's say this is the x-axis, and that's the y-axis, and that's the z-axis. And all of these are orthogonal to each other. And of course, z continues sort of down, right? We have these continuing to infinity. So what here would be orthogonal subspaces? Well, we know that any plane through that contains the origin is a subspace in R3. And we know that any line going through the origin is a subspace in R3. So for example, let's take this plane, the XZ plane. So I'm taking the xz plane, then anything along the y-axis is orthogonal to it, right? Normally when we try to use planes as examples of orthogonality, we do something like this, and then there is a vector coming out from that plane, and we call that vector orthogonal to that plane, or the normal vector. So for those of you who've taken more calculus, or those of you who are going to take calculus, this is what you would denote as the normal vector n or n hat sometimes, depending on the textbook you're using. So the point here is that you can take whatever vector you want on that plane, and it's always going to be orthogonal to the line. Now, looking at when I'm trying to represent 3D space on a 2D page, it might be difficult to see, but think of it as maybe the floor in your room, and then the line between two adjacent walls. So that line is perpendicular to anything on the floor, no matter what line on the floor you would take. And what is important here to note is, and I sort of hinted to that on the previous page, is that you can't have, so two planes in R3 cannot be orthogonal to each other. Now here you might think, well, what if I take one wall in a room and then the other wall in the room, right? And what if there is a 90-degree angle there? Well, what these two planes, so these are two planes that intersect at a line rather than the origin. So this is their intersection, and of course they are infinite, so all of this goes to infinity, but also the intersection is an infinite line. Well, what happens here is that you can take two vectors, right? One vector and the same vector. So let's say we take this vector v, which is in both places. It is in the one plane. So if this is the plane v and this is the plane w, the vector little v is in both v and in w. Well, if this vector is not 0, then it cannot be orthogonal to itself. So if we say that v transpose v is 0, then v must be the 0 vector. Because how do we take, what is this v transpose v? This is the dot product of a vector with itself. So if you have a generic vector with components v1, v2, v3, then v transpose v is v1 squared plus v2 squared plus v3 squared. So if any of these, v1, v2, v3, is non-zero, then the square will be a positive number, right? And the only way to get this combination, this sum to be 0, because all of these things are at least 0 or positive because you're squaring, that means that the sum is 0 if and only if v1, v2, v3 are all equal to 0. So the 0 vector, by this definition, will be orthogonal to every single other vector. Therefore, it must be in every subspace. And therefore, two orthogonal subspaces must only intersect at the 0 vector and nothing more, which is why I was working hard to draw this picture where these two spaces can only intersect at the 0 vector, or the origin if you're thinking of an Rn, Rm type of space. So even though there are many vectors in V which are orthogonal to W, we cannot say that the spaces that these planes represent are orthogonal to each other, because there are vectors along this entire line which are not orthogonal to themselves, right? These are vectors which are along the same direction, therefore they're parallel to each other. So their dot product is never going to be 0 unless you're taking the origin. All right, now we are ready to go to the 4 fundamental subspaces. So when we talk about the 4 fundamental subspaces, let's take a matrix A. And let's say that that matrix is M by N. So what does that mean? It means that the rows of A, so the rows of A have, now remember, M counts the number of rows. N counts the number of columns of A. Therefore, each column of A has M components. So I have A11 all the way to AM1. So you see the first column has M numbers, and then along the rows I go all the way to A1N. So each row, the rows of A have N components, whereas the columns of A have M components. It's a little bit counterintuitive because M counts the rows and all of a sudden those are the components of the columns. But if you just stop for a moment to think a little bit about what these things represent, then you're never going to make mistakes. So from here, I can say that the column space of A is a subspace of Rm, and the row space of A is a subspace of Rn. Now, from the fundamental theorem of calculus, of linear algebra, we also know that the null space of A is also in Rm. Why is that the case? Sorry, in Rn. So I mix these things up. The null space needs to come here. The null space of A is in Rn, and the left null space is in Rm. A quick reminder on how to see this. The null space contains vectors x, which tell us how to combine the columns of A to get 0. And since A has n columns, it means that those vectors in the null space have to have n components. So let's focus for a moment on this fact. Now, again, how do we find the null space of A? Well, we say that A times x is 0. So if A times x is 0, that means that x came from the null space of A. Okay, and remember, the null space of A always contains the 0 vector. But what if the null space of A does not contain the 0 vector? So the hint is that we're talking about orthogonal subspaces. The row space and the null space are subspace of Rn, right? So I cannot really talk about the column space and the row space if I want to talk about orthogonal subspaces, because the column space is in Rm, whereas the row space is in Rn. So these are like living in different worlds, so to speak. They do have something in common. Their dimension is the same, but they live in different worlds, whereas the row space and the null space live in the same world. So why am I going back to this equation AX equals 0? Well, let's talk about how we multiply a matrix. So what is A times X? So the first way in which we defined A times X was, and I just mentioned it again, think of this as a linear combination of the columns of A. But we have four ways of multiplying matrices. And remember, a vector is also a matrix, which happens to have only one column, but you can treat it as a matrix. So we can multiply a matrix times a column, where we represent that as a linear combinations of the columns of A. But we can also use the rows of A dotted with X. So this is the vector X. And let's say A represented by its rows has row 1 here, row 2, and so on, up to row M. It has M rows. So we can find the result by taking the dot product of the first row with the vector X. This gives us a number, and that number will be the first component in the product. Then we will go to the second row dotted with the vector X, and that will be the second component. So the answer here is row 1 dot product with X, row 2 dot product with X, and so on all the way to row M dot product with X. Now, since I chose this X to be in the null space of A, I know that the answer must be 0. And by 0, I mean the 0 vector. So whenever you have A times X is 0, it means that that X must be orthogonal to the rows of A. So we have X as a vector is orthogonal to the rows of A. Now, we just took an X in the null space. We didn't pick on any particular X. It just had to be in the null space. But the null space has infinitely many vectors, right? It can have dimension 1, dimension 2. Of course, it could just be the 0 vector, where we don't really count dimensions. That would be dimension 0. But the point is that I didn't pick on X. I just took it to be from the null space, which means that every vector in the null space of A is orthogonal to every row of A. So every X in the null space of A is orthogonal to the rows of A, right? Because it satisfies this equation A times X equals 0, which can be represented by or through the rows of A. So why does this imply that the two spaces now are orthogonal? Well, remember, we describe spaces through their bases. So really, to say that two vector spaces are orthogonal, it's enough to check that given a basis for the one space and given a basis for the other space, if each element, each vector in the one base is orthogonal to every element in the other base, then we know that the two spaces are orthogonal. So why is that the case? Well, let's take a linear combination of the rows of A. So let's say take, the vector V to be a linear combination of the rows. So to be C1 times, let me just use R1 for shorter, but that means row 1, plus C2 row 2. And think of rows as column vectors, plus CM row M. So these are all column vectors, and I take a linear combination. So this means I'm taking a generic vector, an arbitrary vector in the row space of A. So remember, the row space of A is the space of all linear combinations of the rows. So I'm just taking any linear combination because I have not specified what C1, C2, all the way to Cm need to be. So now I'm going to take the dot product of X and V. So that is X transpose V, right? I could take V transpose times X, but let's take X transpose times V. So that is X transpose times C1 R1 plus C2 R2 plus CM RM. Now, we've mentioned many times when we have matrix multiplication, we can't just rearrange orders here, right? But C1, so just focus on the product X transpose C1 R1. C1 is a number. It's a scalar. So C1 can be moved to the left, to the right, it doesn't matter. So just with scalars, we get to move them around. And the same will be true for the second and the nth component. So really here what we have is C1 X transpose R1, and obviously we want to focus on X transpose R1, plus C2 X transpose R2 all the way to CM X transpose RM. Now, if you focus on your attention here, I'm talking about the dot product of row 1 or R1 times X. So normally we would write that as R transpose X, but the dot product is commutative. So if I have, so in some sense, U dot V is the same as V dot U, just because of how number multiplication works. So if row 1 times X is 0, if the dot product of row 1 and X is 0, then X transpose row 1 is also 0. So don't worry about the ordering there. So you see you have C1 times 0 plus C2 times 0 plus CM times 0, and all that adds up to 0, and these zeros are the 0 vector. So what this means is that if the vector X is orthogonal to the basis of the row space. Now, it could happen that the rows here are not linearly independent, so they may not represent a basis, but they contain a basis for the row space. So the basis, so you can take a basis in here if you just take the pivot columns. So it doesn't hurt to take more vectors, but you have at least the basis. So if X is orthogonal to each basis vector, then X must be orthogonal to any linear combination of those vectors. Or I can completely remove the word basis, but it's just a hint on how to check for two vector spaces and their orthogonality. The easiest way would be if you have a basis for each, you want to check orthogonality between the basis vectors of your choice. But otherwise, if you know that a vector space is spanned by R1, R2, all the way to Rm, then if you have another vector X, which happens to be orthogonal to all of those vectors, then that X will be orthogonal to any linear combination. So the big statement here is that the row space of a matrix is orthogonal to the null space of that matrix. So row space and null space are orthogonal. Now, the same is true for the column space and the left null space. And it's very, here we see this notation that we use with the transpose. So when I say row space, I'm actually talking about the column space of A transpose, or I can say I'm talking about the column space of A transpose. And it's very convenient here because I can say that the column space of A is the row space of A transpose. So you see this statement, the fact that these two subspaces are orthogonal to each other, follows from the statement that these two subspaces are orthogonal to each other. So let me write that. Now we have shown that the row space of a matrix is orthogonal to the null space of that matrix. Now, from here, we also have that the column space of a matrix is orthogonal to the left null space of that matrix. How can you see this? What's the easiest way to see this? Well, let the matrix B equal A transpose. Then B transpose is A transpose transpose, but that's just A. So when you transpose twice, you go back to the original thing. So then the first statement, column space of B transpose is orthogonal to null space of B, translates into, is the same as the column space. So remember, B transpose is A, is orthogonal to the null space of A transpose. So just doing that first statement for for A transpose gives you the second statement, but that completes the picture. So really, the big picture that we have about the four fundamental subspaces is that in Rm, so here is Rm, no, sorry, that's Rn. I'm trying, it's very important to be careful here. So the row space and the null space, these are subspaces of Rn, whereas the column space and the left null space are subspaces of Rn. So here I have the picture Rn. Okay. Now, in Rn, I have the row space, of A, and that row space is orthogonal to the null space. They only intersect at the origin, at the vector 0, and they are at 90-degree angles. So if you take a row and you take an element from the null space of A, the dot product of those two vectors will be 0, which means they're orthogonal, they're at 90 degrees, and so on. Now, the dimension of the row space, this is very important. So here, the dimension is R, which is the rank, and the dimension of the null space is n minus R. So we'll define this in the next video very precisely, but we see that kind of everything that's not in the row space is in the null space. Now, when we apply matrix multiplication, what happens is that the row space gets transferred into the column space. So remember, when you take A times X, so if I take an X in the row space of A and I multiply, I'm going to get a B. Whereas if I take A and multiply it by X in the null space, I'm going to get 0. So the way to get something non-zero is to take a vector from the row space. The way to get a 0 is to take a vector in the null space. So this AX equals B, now remember, B is a linear combination of the columns of A, so this B is in the column space. So we have the column space here. This picture is in Rm. We have the column space of A. And that space is orthogonal to the left null space. The dimension of the column space is again the rank R. The dimension of the left null space is M minus r. So let me repeat this one more time. Matrix multiplication can be thought of as a transformation. We take a vector in the row space and we find a vector in the column space. So this B is a vector in the column space. If you take x in the row space, then you know that at A times x is not going to be 0. So you're coming to the column space. Now, if you take a vector in the null space, so I should mention here, I could take x equal to 0 because 0 is both in the row space and in the null space. But if I take a non-zero x in the row space of A, I'm going to get a non-zero b in the column space of A. So we see that multiplication by A transforms the row space into the column space. And it transforms this entire null space into 0. So then, where is the left null space? Well, we can find it with A transpose trying to go back, or just as the orthogonal complement, which we will define in a minute, to the column space of A. The very important observation here is that the dimensions m minus r and r fill up Rm. So you have dimension r, dimension m minus r. The only thing that these two spaces have in common is the 0 vector and nothing else. Well, if you take if you take a basis for the column space and the basis for the left null space, you're going to have m linearly independent vectors from Rm, and they give us a basis. And similarly, if I take a basis for the row space and the basis for the null space of A, then I will have n linearly independent vectors because I have r many in here and n minus r in there. So together they give me n linearly independent vectors, which can be a basis for Rn. All right, with this, I'll stop and we'll continue in the next video.